So again, a way to describe those is they are C2 epimers of one another. So the D part of the sugar stays the same. The carbon 2 can be S or R. So then for each of those, you can repeat the process from a tetrose, then make the pentoses, and that's how you elongate the chain to make those different families. Any questions? So say you don't like adding things, you like taking away things, you're a capitalist. So the next reaction is called the rough degradation. Strategically, it works kind of the same way in that you're only operating at the top of the chain. So the rough degradation is a two chemical step strategy. The aldehyde carbon gets oxidized up to the carboxylic acid. So that's the aldonic synthesis there. So you're at oxidation state 3 now. And then you're going to treat with iron sulfate, hydrogen peroxide, and water. And it's going to cleave the C1 to C2 bond. And then that C2 carbon, that gets oxidized from oxidation state 1 to 2. And the carbon that was 1, that gets lost as carbon dioxide. So that's a chain degradation. And then obviously that can be repeated. You can shorten it again and again. So Kiliani-Fisher will add a carbon, the rough degradation takes one away. And again, notice through that second step, the stereochemical information here at that alcohol is destroyed because that now is an aldehyde. But the other two centers, they remain the same. So nothing happens to them. So again, using a bit of the logic, which pair of sugars, when oxidized to alderic acids with nitric acid, will become meso? So this is when the terminal carbons become the carboxylic acids. So you're looking for that internal mirror plane of symmetry. Yeah, so C. It's essentially the same answer as when you reduced them with the alditol synthesis. So now you're just oxidizing those terminal carbons up to the acids. Alditol reduces them down to alcohols. So allose and galactose, and we said the mirror plane was between carbons 3 and 4. So what two sugars, when oxidized to alderic acid, so again, both carbons 1 and 6 go to the carboxylic acids. converge upon the same identical compound. So B, that was altros and talos. And the thing with that is one of them you have to rotate 180 degrees so then it maps onto the other one. And then finally, again, the alderic acid synthesis, which pair will have 180 degree rotational axis? Yeah, so that was mannose and idose. And so now the rotational axis is not a mirror plane. It's sort of you plunk a dot and then you rotate it. So that dot for mannose would be right here. And then idose right there. So what can I say about that before we move on? That was some of the logic that Fisher used to help prove what the structure of glucose ultimately was. Again, associated with these signs. So when those things converged upon meso compounds, what's the specific rotation of a meso compound? 0. So through a series of logical steps, through chain elongation, degradation, he was eventually able to figure out which of those hexoses was glucose. Any questions? So now we'll move into polysaccharides. And so these will be presented to you in the form of the repeating unit of the monomer. So these polysaccharides we can think of as biopolymers made of carbohydrate monomers. So the first one here is called cellulose. And the naming of it, if you're a nerd like me, you'll enjoy figuring out the name. I'm not going to go too much into it. O stands for oxygen. Alpha or beta stands for that anomeric center. The D or L tells you if it's natural or an unnatural sugar. The front part, that tells you which sugar it is. This last part tells you the ring size. So pyran is a 6-membered ring. A furan is a 5-membered ring. Those are the most common ring sizes. This thing in the middle here is telling you which oxygen atoms are linking the two sugars of that repeating unit. So cellulose has basically 2 molecules of glucose linked together from this number 1 carbon atom to that number 4 carbon atom. And the sugar to the left, that's normally how sugars are presented, in that chair with that oxygen right there. This is still glucose, but it's kind of been rotated 180 degrees, so that's why the oxygen's in the front. You can tell it's glucose because all of these alcohols are still equatorial. So natural materials that have this polymer in it are cotton. So cotton's 90% cellulose. Wood is 40 to 50%. Hemp is 55%. So I would wager that not many people in here are wearing like a pure cotton shirt or pants. It can be pretty uncomfortable, especially when it's hot and humid. It doesn't allow heat to escape very well. So most shirts are like a blend of fibers now. You have sort of a natural fiber and then a synthetic fiber. So things that are stretchy or like dry fit shirts that wick away sweat. Like if you were wearing a straight cotton shirt and you were sweating in it, you'd be very uncomfortable. So these sort of natural materials mixed with synthetic ones make for different, feelings of clothes on your body, for lack of a better way of putting that. So that's cellulose. Chitin is a derivative of glucose, but now when we look at the name, an OH group has been substituted. So we have an amino group that's been acylated, so this is called N-acetyl. Glucopyranacil. You see that similar 1-to-4 linkage there. And so chitin is a component of cell walls in fungi and exoskeletons, such as crustaceans and insects. So you ever have the unfortunate experience of having like a cockroach in your dorm or apartment or something? You try to step on it, and what does it do? It laughs at you and runs away. So that shell is really, really strong. So, I mean, you really have to smack it with a hammer or something to get rid of it. So the chitin is what gives those things their strength. So starch is now still made of 2 glucose units, but look at the linkage here. So from 1 to 4, so there's 1, there's 4, it's now an alpha linkage. Starch can have a linear form, or it can start to twist back on itself to form a helical form. And we'll talk about those sort of tertiary or secondary shapes when we get to peptides and proteins. So where do you think you've seen starch before? Huh? So potatoes, when you take, if you're cheap like me, you buy your Barilla pasta or your Great Value pasta, you throw it in the boiling water. It gets cloudy. So that cloudiness is the starch that's coming off your pasta. So again, it's, if you boiled your sweater, which is made of cellulose, it's going to get wet, but it's not going to disintegrate. So the cellulose and starch, that anomeric configuration makes a huge difference in the properties of the molecule. So those were a couple polysaccharides, mainly focused on the glucose monomer. You can have any other sugar be a monomer in there, and they have different forms and properties. What I want to talk about now is taste. So specifically the sweetness receptor. Taste is a perception of sweet, sour, salty, bitter, or umami. So that's savoriness. So like when you're eating meat or a steak, you would use umami as a way of describing that perception. And this word is interesting, right? Because, there's however many different human beings in this room. We all perceive things differently. And that's what we're going to do today is you're going to taste 6 different things. Those are the same things. That's the control, but you're the experiment. How is your perception of that taste different? So if you go onto biochem, you'll learn about, these biochemical cycles or metabolic processes. So what are the enzymes involved in the perception of sweetness? So the taste receptor type 1 member 2, TAS1R2, is a protein encoded by the TAS1R2 gene. And I'll let you look at that 1, 2, 3, 4, 5 lines of stuff that's happening. So you start off the molecule, you put it on your tongue, the molecule binds to a receptor, a conformational change is triggered, G protein is activated, taste bud is innervated. So, that happens pretty fast, right? Like as soon as something hits your tongue, you taste it. But all of that stuff's happening in that short amount of time. Just like with vision. Light travels at the speed of light, it happens. All this stuff happens nearly instantaneously. But what's the important part? Emotions. So with my kids, are you mad or happy or sad? So when you taste something, does it taste good? Does it taste bad? Do you want to eat more of it? Do you want to eat less of it? What's the emotional response? So that's a driving force for why we don't just wither away and die, right? Because you're hungry, you want to eat something tasty, that gives you your glucose, you metabolize it, it gives you your energy to get out of bed and come to organic chemistry at 1 in the afternoon. So let's just calibrate ourselves on some structures before we do some testing here. So disaccharides, again, are 2 monosaccharide sugar moieties linked through the anomeric carbon. So that's the important part to realize. The anomeric carbon was the acetal. Now, when we look at that acetal here, we have oxygen and then carbon, oxygen and carbon. That carbon is no longer a reducing sugar because there's no OH group bonded to that acetal. And so the structure that you see there is table sugar. So your common sugar, it's sucrose. So through the action of an enzyme, so either alpha glucosidase or beta sucrase. So here's the glucose part. This is the fructose part. Those enzymes will cleave the anomeric CO bond. So you end up with a molecule of glucose and then a molecule of fructose. So notice how that name changes. It says furanose now. So furan means the 5-membered ring. And see the beta carbon? It's right there. That's the anomeric carbon. It's oxidation state 2. Now, when you look at what's bonded to it, is that equivalent to an aldehyde or a ketone? What? So that's equivalent to a ketone. So there's the carbon, there's oxygen. So that makes it oxidation state 2. Now, when we look at everything else, carbon and carbon. So this is equivalent to a ketone. Here's a bag of table sugar. At least I think it's table sugar unless I grabbed the wrong bag. It's a little joke there. This is 65 grams of table sugar. So that's kind of what's in your average Coke bottle that you get out of the vending machine. So is that a lot or not? It's quite a bit, right? More than probably any human needs in one day, right? That's just in one bottle. So you would be hard pressed to find a naturally growing food that has that much sugar in it. So, you can debate about why so much of that is added. There's talk of tariffs and all this stuff. So sugar's added to stuff because farmers grow it. They need to sell it, make money, so they put it in food. That's one of the reasons why it's added. But table sugar is an interesting molecule in terms of the development of our country here in terms of a crop. So how does the fructose form? Well, basically you take glucose and you tautomerize it. So remember, that was a shift of a hydrogen atom from carbon to oxygen. So this H then migrates up to there. And then through that process, you get that alkene. And then you get a second tautomerization. This H will then migrate over to that carbon. And so now that generates the ketone. And so it would be that alcohol. So remember, that was the penultimate alcohol. If that cyclizes onto there, that gets you a 5-membered ring now. So those type of isomerizations are important in biochemistry, where you're basically moving the carbonyl group up and down the carbon backbone. And it therefore allows you to form different ring sizes. So that was table sugar, again, a molecule of glucose with a molecule of fructose. Lactose has the C4 epimer of glucose, that's called galactose, linked from carbons 1 to 4, so a galactose to a glucose with that beta linkage. And lactose is perceived as being 0.3 times as sweet as sucrose. So it's less sweet. Any questions? So maltose now is 2 glucoses, and they're linked through an alpha linkage. So again, carbons 1 to 4. And then maltose has the sort of same sweetness perception as lactose. It's not as sweet as table sugar. Questions? No questions. So those are naturally occurring sugars, and again, you digest them. They'll produce either glucose or galactose. There are things called artificial sweeteners. So these are added to increase the perception of sweetness without adding the caloric, It's the word I'm looking for, without adding as much calories to your diet. So the benefit of that is your liver doesn't have to process all of this. So you can add a little bit of something else that still makes it perhaps enticing to eat, but then you don't have this liability of processing all this. So high fructose corn syrup is added to a lot of things, again, because it's a subsidized product, but it has all these negative health impacts. So these other molecules, which are artificial sweeteners, are added as a replacement, and the benefit of those is they're not metabolized the same. They don't have the same negative health benefits. So shown on this slide here is sucralose. A brand name for that is Splenda. So one of these is, I guess we do have Splenda in I bought the good stuff. I didn't cheap out and buy the cheap stuff. So that looks like table sugar, but what's different? So I'll highlight here in yellow. So you've taken some of these OH groups and just substituted them for chlorine. So your typical SN2 type reaction. And so that poses an interesting question about the perception of taste. You've gone from a hydroxyl group now to a chlorine, and that's increased the sweetness quite a bit. So your tongue is actually a sensor for chemicals. I mean, that's what taste is. It's a chemical hitting a receptor, goes through all that process, and then you have an emotional response about it. So here are some common artificial sweeteners. So saccharin, which is sold as sweet and low. That's about 200 times as sweet as table sugar. Sweet 1, which is acylfem K. We saw sucralose already. Equal or NutraSweet is aspartame. It's about 200 times as sweet. So equal is, if you look at that structure, it's made up of 2 amino acids. We would call that a dipeptide. Then if you look at the other derivatives, neotame and advantame, see this NH2 here? One of those has been substituted for this sort of, I would say, fatty carbon chain, lipophilic carbon chain. And then you've done you've done the same thing over here, but now you have an aromatic ring. So you have some sp2 hybridized carbons in there. It's maybe a little bit more flat. But look at the jump from that NH2. You've substituted it's now perceived thousands of times more sweet. Unfortunately, Walmart or Amazon doesn't sell that. I would have bought some if possible. I can buy it on eBay, but then it's shipped internationally, and I don't want anyone getting poisoned by some substance I got in the mail. So these are all bought from Walmart. There's no worries about tasting them. So those were synthetic or artificial ones. There's also these natural artificial sweeteners. One of them is stevia. You might have heard of that. And so it comes as this steviol glycoside. And what that is you have this foundation or platform that's hanging on to these glucose molecules. And these naturally artificial sweeteners are put in a category called generally regarded as safe or GRAS. And the FDA allows those to be used because historically people from different cultures will take plants, soak them in water, drink that like tea. If you identify what that stuff is in the tea, and the FDA says, yeah, people have done this for thousands of years. You don't get like brain cancer or anything from it. So we'll let you put it in to a food product without having to do sort of your normal pharmaceutical testing. So the heavy hitters here, these are all based on a functional group called a guanidine. So that's this central functional group there. That's common amongst all three of them. You're just changing out the other substituents, and now you're up into like the hundreds of thousands. And I'm semi-adventurous. I would try one of these to see if my face melts by tasting something so sweet. But that's, again, if it's a perception, how do you make a scale for people to perceive that? You know what I mean? How do you know it's quantifiable as that? So those are obviously not used in any food product that I'm aware of. And okay, so here we are. We're at the taste testing now. If you don't have a sheet, come up and grab a sheet from me. Did you get a sheet already? So you have 6 packets. Please be very mindful. This is a community classroom, and don't rip it open and shoot the powder everywhere. Dip your finest Coke nail in there and taste it. When you're done, please throw the trash in the bin in the middle there. Please don't leave a mess, otherwise I'll get in trouble. I don't like getting in trouble, so let's go ahead and start. So start with the sugar and the raw. So give it, don't pour the whole packet in your mouth because you have 5 more to taste. Just do a little bit. When you're done, how do you perceive it? There's some fancy words for you. Yeah, so this is question 1. So respond A, B, C, or D for sugar in the raw. What color is the crystals or the powder? What? Brown. Yeah.
When you say that technical art electrical is less expensive,
That's for.
I think delectable is better.
That's for your interpretation of how you perceive it.
Because when I say pleasant, I'm like,
So it's the sugar's brown, right? It's what other word is on there? Turbinado. What's the Shake Shack, Shake King? What's that place called? By Qdoba? Not Steak and Shake. You get the Smoothie King. There you go. Smoothie King will tell you that, their shit's sugar-free. This is what they're putting into it. So, do you? So, okay. So, turbinado is sugar that has not been as refined. So that's where the color is coming from. So the color comes from like molasses. It just hasn't been fully purified out of it. So go ahead and finish up your question 1 here. How do you perceive it? And so let's now look at the domino. So what color is the domino sugar? It's white. The domino sugar comes from the cane sugar. It's been purified more. So all of those other things have been purified away. So sugar can come from sugar cane or sugar beets. Those are crops that grow very well in the southern part of the U.S. Again, I'm a New York Times reader. Don't infer anything political about that, but the New York Times has some nice articles about the history of sugar plantations in the U.S., and it's pretty interesting. I mean, it's a raw sort of resource. The processes are well defined now, but 100 years ago, they're pretty brutal conditions to get sugar in either that raw form or the refined form. So go ahead and finish up your question 2 here on the domino, and then next up is the stevia. Yeah. So I've done this for like 3 or 4 years now, and I would say most undergraduates, that's the common response, is that this is the worst tasting one. Do you have a question?
Salt on your tongue for like whenever you're gonna throw up, and it helps you not throw up. Yeah. This is exactly what that tastes like.
There you go. So again, when that hits your tongue, and does it taste bitter at all? Yeah. So, like these sort of natural products that come from plants, that's typically the word that's used, the bitter constituents. I mean, this is the sugar part. I mean, it's on your tongue, it's cleaving those sugars off, and you're tasting that bitter constituent. And again, it happens like instantaneously, right? So these things happen, as soon as you perceive it, it's done. So go ahead and answer question 3 here. So those were the natural ones. So now we're on to the synthetic ones. Here's sweet and low. So go ahead and take a swig of water, wash away the sins here, answer question 4, and then we'll move on. So we'll try the equal next. That's the asulfam K. So the blue one. All right, so we'll finish up number 5 here and then move on to the last one. That's the Splenda. What did you say it tastes like? What is B? Halcyon? I think it means heavenly. So go ahead and record your answer for 6, and then we have a couple more questions here. Again, the point of this was, to use your tongue as your taste of those different structures and how do you perceive it. So the next question here, of the 3 natural sugars, which one was the most pleasant to you? Okay, so next question, of the 3 artificial sweeteners, which one was the most pleasant to you? Okay, so last question, what do you prefer, the natural or artificial? So please make sure that you've filled in your ID, the numbers and the bubbles. I think we're going to wrap it up here today before my voice goes. So throw your garbage away and then come up and hand me your sheet, and then you can head out.
That was fun.